All right. In today's experiment, we're actually not really running an experiment. What we're doing today is we're actually going to be looking at how to build molecular models so we can actually look at the three-dimensional structure of chemicals. You know, when we've been drawing molecules on paper, writing out reactions to this point, everything we've been doing has been very two-dimensional, very flat in the plane. But in reality, molecules have a three-dimensional nature about them. You know, if you think about it, everything around you is three-dimensional and is all made up of chemicals and molecules. So therefore, it's quite logical that somehow these must have some kind of three-dimensionality to them so that they can actually create these kind of structures. So, you know, as an example, we've drawn water a lot. If I just quickly make a model of water for you, you'll understand what I'm talking about. So if we build water here, and we'll go through what I'm doing in just a moment. All right, so here's water. As you can see, that's fairly two-dimensional in its own right. But if I were to take this and make one more molecule, so if I make methane instead, which is just a common gas, and you might have seen this already if you've been working on this in your class, you can see that this molecule is clearly not two-dimensional. So this is methane as we understand it to be. Notice how these three here kind of form a little pyramid that it can stand on as you're looking at it. If I just turn this sideways, you can kind of get a sense that this is not in the plane anymore. These two are going away, these two are coming up at you, and ultimately what we have here is we have a methane molecule that is three-dimensional in nature. When we write it on paper and we write CH4, you'll notice that we actually don't show that dimensionality. We just write CH4, so we don't get a sense of what it's like in real life. So this section of work where we talk about Lewis structures and we get into valence shell electron pair repulsion theory, sometimes known as VSEPR, once we get into these two pieces, we can start understanding how molecules are situated in terms of where the different atoms are, and ultimately what kind of dimensionality they have. So I'm going to just pull these apart real quick so we have these to use in a few minutes. So here and there in this video, I'm going to take a couple of seconds to kind of break apart the molecules that we've been making. But that was just a quick show so you understand that molecules are three-dimensional in nature. And we're going to look at a lab, so we're going to start working through some examples of this and try to understand exactly how to determine which atoms are in the middle, which are on the edge, what kind of bonds exist between them. So let's work through an example first of all. So first thing I'm going to do is we're going to look at the molecule methane. So methane has the formula CH4. The first thing we need to do is determine how many valence electrons are present in each. So you should at this point be able to determine valence electrons. You should know how many valence electrons are present in a given atom by looking at the periodic table. Basically, if you look at the group number at the top, the ones that are labeled A with the Roman numerals, that will tell you how many valence electrons you have, at least for the main group elements. So if we look at carbon, it's in group 4A. So carbon has 4 valence electrons. And if we look for hydrogen, hydrogen we know has 1 valence electron. Then what we need to do is we need to understand how many of each element are present in our molecule. So the carbon, there's no number following it, so its default is 1. So we're going to just multiply those 4 electrons by 1. And the hydrogen we're going to multiply by 4 since there's 4 of them in the molecule. If we do the math on that, we have 4 valence electrons contributed by the carbon. We have 4 valence electrons contributed by the hydrogen. That will give us a grand total of 8 valence electrons in total contributed by the 5 atoms total that are present in this molecule of methane. And it's these 8 electrons that we're going to use to construct the geometry of our molecule. So then the next question you have to ask yourself is, so the first step here is number of valence electrons, right? That's the first thing you need to calculate. So that's sort of a step 1, if you want. Step 2 is to determine what is the central atom. which atom is going to go in the middle? When I built that methane, I already built this for you, we knew that carbon was the central atom. As a general rule of thumb, the least electronegative element is the one in the middle. Now, sometimes that's the hydrogen. The hydrogen cannot go in the middle because it can only form one bond, so it will always have to be on the outside. So my recommendation here is to consider the least electronegative element to be the central atom, except, of course, hydrogen. So technically, in this instance, the hydrogen might be a little less electronegative, but the reality is the carbon is the central atom here. So we're going to put, then what we're going to do in step 3, we're going to put our central atom. So in step 3, we're just going to arrange the atoms. We're going to put carbon as our central atom, and then we're just going to arrange the 4 hydrogens around it. I'm just going to put them roughly equal distance apart. So now we've arranged our atoms. The question now is, what kind of bonding do we have? So we know how many valence electrons we have, and we know these electrons are the ones that are going to build the bonds between these atoms. Remember that every bond has 2 electrons. So now we're going to start, we build single bonds. And it's important that we start with just single bonds. So we want the minimum connectivity between all the atoms, between the central and the peripheral, so the ones on the outside, atoms. So notice it's just single bonds. We're not building any double bonds. That all comes later if they're present. And remember that every bond has 2 electrons in it. All right, so single bonds have 2 electrons. So once we've placed these single bonds in place, we have to account for those bonds. So we're going to draw a bond here between a central and peripheral atom, central to peripheral atom here, central to peripheral here, and central to peripheral here. Now we've connected all the atoms together through that central atom. And it's important that we do this because if we don't, they're not a part of our molecule. Now, we've just built 4 bonds. We said at the beginning that we had 8 valence electrons that we could use for our structure. Each one of these 4 single bonds contains 2 electrons. So, if I now say we start with 8 valence electrons, we just built 4 bonds, and we know that each bond is 2 electrons. That gives us 8 electrons. We started with 8, we just used 8, so we technically have no more valence electrons remaining. So as we're building this structure, we need to keep track of our valence electrons and make sure that we haven't used more than we've got. There's no such thing as electron credit, right? This is like a bank account. We start with so many electrons in our bank account, and as we spend those electrons building the structure, we'll eventually get down to 0. You can never have negative electrons, obviously. So we've used all of our valence electrons, so that's okay. Now we just need to make sure that our structure actually holds true. So in step 5, what we do is we check for full valence shells in the peripheral atoms. Now usually we are checking for 8 electrons, right? The octet rule. Except, of course, the classic example being hydrogen, which is 2 electrons, and boron, which is sometimes going to be 6 electrons. But usually we're looking for 8 electrons. So let's look at our peripheral atoms. What we see is we have 4 hydrogens. So we're going to check this hydrogen here, and we're going to think about how many electrons are in the sphere of that hydrogen, as it were. And that includes the bonds. So right now, I'm not showing any lone pairs around this hydrogen. I am showing a bond connected to that hydrogen. So the 2 electrons in that bond are effectively associated with that hydrogen. So I can say there are 2 electrons inside that sphere, and that 2 electrons for hydrogen So I just realized I wrote off the page. The 2 electrons for hydrogen, like I talked about a moment ago, is a 4 valence shell. So this hydrogen is good. Now each of these hydrogens is the same, right? It has that bond in it. So they each have 2 electrons. So I can comfortably say that each of these peripheral hydrogens has a full valence shell, and they're satisfied. The last step, which is step 6, is to check for full valence shell of the central atom. Same rules, looking for 8 most of the time, but with you can't have hydrogen in the middle, but if boron was in the middle, you'd be looking for 6, that would be okay. And we'll have some tweaks on this later on, but this set of rules will hold up pretty well. So now if we look at our carbon, if we look at what's attached, the carbon has 1, 2, 3, 4 bonds. So if I draw a circle that kind of encompasses those bonds for the carbon, inside that sphere of carbon, I have no lone pairs written on my carbon. You'd see them because I'd write 2 dots. Instead, what I do have, though, are these 4 bonds. And we know that every bond contains 2 electrons. So technically, in that carbon sphere, we have 8 electrons. That is a full valence shell for carbon, so the carbon is also satisfied. So now we're at a point where every element has a full shell, and all the valence electrons have been used. And so this is actually a satisfactory Lewis structure for methane. So we can comfortably say that when we want to draw up methane, at least in 2 dimensions, we can show the connectivity and the bonding that exists by going through this method. So there are 6 steps, and we just have to work through them slowly. So finally, if I wanted just to redraw this so it was clear, my Lewis structure for methane would look like that. The carbon would be in the middle, and the hydrogens would be around the outside, and they would all be connected by single bonds. This is a perfectly good Lewis structure of methane. So now let's build this so we can actually see the dimensionality of it. So I'm going to leave that just in shot so we can see it. Now what we're going to do is we're going to find our carbon atoms. Carbons are usually represented by the black spheres in the molecular modeling kits. We're going to get 4 single bonds because that's what we said we needed. So there's the 4 single bonds. And then hydrogen is usually represented by these white spheres. So we're going to get 4 of those because we have 4 hydrogens. So we have everything we need now to build our methane molecule. We've got the 1 carbon atom, the 4 hydrogen atoms, and the 4 single bonds between them. We said the carbon atom was in the middle, and it had single bonds attached to it, so we'll build that first. I know I've already shown you this one, but we're just showing you how to go from a 2-dimensional picture that we have into a 3-dimensional molecule. So there's our carbon with the 4 bonds, and now we're simply going to attach our hydrogen atoms to these. These atoms are not perfectly to scale, but they kind of give you a sense of the different sizes of the atoms. And you don't have to use white and black, but these are fairly standard. You do need to make sure that your atoms have the right number of connection points. Hydrogen only has 1 connection point. Carbon can have up to 4. So this is methane as it is now drawn. So if you were doing this as a lab, for example, your instructor would now come and check and make sure you've built your methane molecule correctly. Carbon atom in the middle, 4 single bonds attached to hydrogen all around it. Now the next question you get asked, because you're moving now into VSEPR, the valence shell electron pair repulsion theory, is what kind of molecular geometry do we have? Now we're looking at it, so it'd be easy to tell. This is where you'd use a reference table to try and figure out what kind of molecular geometry this is. So I'm going to do this one for you, but on future examples I'm going to allow you to look that up and figure it out. But if you look this up on a table, it will tell you that this is a tetrahedral structure. So tetrahedral is basically a triangular base pyramid, right? You have the triangle base here, and then if you look at it from the side, you can build a pyramid from that base to that peak, kind of like the ones in Egypt. Except the ones in Egypt are a square base pyramid. They're a little bit different. So this is basically a triangular-based pyramid, but the technical term is a tetrahedral molecular geometry. Now, once you've determined what kind of molecular geometry you have, you can then determine the angle between two of these bonds. Now, normally, when we're thinking about angles on a page, it's in 2 dimensions, but this is in 3 dimensions. So this is a little more difficult. This bond angle here is one of the classic bond angles. And in methane, this bond angle in a tetrahedral structure is 109 degrees. So if I'm writing this on my paper, this angle that goes from a hydrogen to the carbon back out to another hydrogen, that angle there is actually 109 degrees. And that measurement right there, or that angle right there, is dependent very much on the kind of structure you have. You know, if you draw a triangle with 3 equal sides, 3 equal angles, each of those angles will be 60 degrees. If you draw a square, 4 equal sides, 4 equal angles, you know that angle will be 90 degrees. So the different geometry will dictate a different internal angle for that structure. Well, the same is true of molecules. As we build different molecules, you're going to see they don't look exactly like this one, but that is 109 degrees. If these were in the plane, if it was 3 items in the plane, that angle would be 120. We might actually see one of those structures as we do, but for the moment, you should be able to look up the structure in the table and you'd find this is tetrahedral. It has 4 electron domains, as it were, and they are all connected to bonds. Therefore, not only is the electron domain structure a tetrahedral, but the actual molecular geometry, the one dependent on the actual bonds formed, is also tetrahedral. So the other thing you might need to look at is bond polarity. So bond polarity is dependent upon electronegativity. So if we have C attached to H, the question is, if there's 2 electrons in here, if these are shared between the 2 atoms, the question is, are they right in the middle or are they to one side or the other? If this was a carbon to carbon bond, those 2 atoms are exactly the same, and so we would anticipate most of the time those electrons are roughly living in the middle of the bond, but they're moving all the time, but just on average they're in the middle of the bond. Between the carbon and the hydrogen, there's actually now a difference in their ability to attract those electrons, and that ability is referred to as electronegativity. Electronegativity is the ability of either one atom or the other to attract the electrons that are present in a bond. Whichever one is better at attracting them has the higher electronegativity. So when we look at carbon-hydrogen, we can figure out whether the electrons, we know the electrons wouldn't be right in the middle because these 2 atoms are different. Therefore, they have different electronegativities normally. And so those electrons are going to exist a little bit closer to one side of the bond or the other based on that electronegativity. Now, the carbon is actually slightly more electronegative than the hydrogen, and as such, those electrons won't be right in the middle. They'll be a little bit to the left. So if there's any kind of bond polarity at all, it is going to be towards the carbon. It means the electrons have moved more towards the carbon, so we draw the arrow in that direction, and we draw a little crosshead on the other to show the actual dipole. So this is the bond dipole for carbon-hydrogen bond. The carbon is just that little bit more electronegative than the hydrogen, and so therefore we would draw the dipole in this way. So from a bond polarity perspective, the carbon-hydrogen bond is slightly polar, very slightly polar. It's not considered a polar bond, but the dipole would point towards the carbon. Now what we need to think about is, how does this impact our whole molecule? If we have a 3-dimensional molecule like this, and we know that each bond is pointing towards the center in terms of the polarity arrow or the dipole moment, if they're all pointing towards the center, what's the overall effect of polarity on this molecule? Well, if they're all pointing towards the center, that means the entire outside is positive, and the middle part is a little bit negative. So if I were looking this from the outside and was just rolling this molecule around in my fingers, if I can't see the carbon, all I would see is like these bits of positive nature around the outside. There's no overall polarity. There's no one direction in which you can look at this and say, oh, it's a little bit negative in that way and a little positive in that way. No, all we would see is positive. Another way to look at this is sort of a vector sum. In 3 dimensions, if I were to draw 3 dipoles or 4 dipoles following 109 degrees in 3 dimensions, it would be hard to, you can't obviously draw in 3 dimensions, but we would end up coming back to where we started. So our net vector would be 0 of these 4 dipoles. So whichever way you look at it, whether you can see a charge on a surface or whether you can add the 4 dipoles together, if you come back to the same spot, there is no net dipole, which means it's non-polar. If you were to do this and you came out and there was like a gap between the beginning and the end, then you would say there is a net polarity. And we'll do one of those as well in a moment, and we'll see what that looks like. So if I were doing methane, if I were working through this from start to finish, the first thing I'm going to do is figure out how many valence electrons I've got, which is 8 in this case. I would then, using our standard steps here, I would then work through figuring out the central atom and the peripheral atoms. I would arrange those atoms the way I thought. Then I would build single bonds between each of them, and I would account for those electrons to make sure I have enough to do that. And then what I would do is I would check to have my 4 valence shells in the peripheral atoms first. And then once I've done that and got them happy by adding lone pairs, then I would check the valence shell on my carbon, and I would make any adjustments I need to as we go. And we're going to do more of these, and I'll stop. Some of them you're going to do more of the work, and some of them I'll do a bit more of the work to show specific examples. But I wanted you to see very straightforward examples. So then we eventually end up with this 2-dimensional version of a Lewis structure. And then we built the molecular model so we can see the 3-dimensional structure. Now we could predict this shape by using a table of VSEPR geometries, or we could simply build it like this so we have a much better sense of what it looks like. Once we've got that structure, then we can determine the bond angle between different atoms that are present. In this case, it's all the same bond angle, so it's just the one angle. And then we can figure out whether or not individual bonds have a dipole. And then by considering either the vector sum or what it looks like from a geometric perspective, we can then determine whether or not the molecule is polar or nonpolar, and methane is nonpolar. Excuse the writing there. And so this is like a full workup of a single molecule, and it won't always take this long. It wouldn't always take this long to explain every single little step, but I do want you to understand the full procedure going from the beginning to the end of building one of these molecules. All right, so we're going to put this molecule away for the moment. And what we're going to do is start looking at the next molecule. Next molecule we're going to do is we're going to do the molecule carbon disulfide. Carbon disulfide has the structure CS2. So when we look at carbon disulfide, the first step is to figure out how many valence electrons we have present. So we have a carbon atom, we have a sulfur atom. If we look in the periodic table, we can find that carbon has 4 valence electrons, and we can find the sulfur has 6 valence electrons. Then we have to figure out how many of each atom are present in our molecule. Well, the carbon, there's clearly 1, and the sulfur, there's 2. So the number of valence electrons contributed in total, it's going to do a little bit of simple math here. You got 4 valence electrons contributed by the carbon, and you have 12 valence electrons contributed by the sulfur. In total, we have 16 valence electrons that we can use to build our structure. The next step is to figure out roughly how the structure is going to look. Which atom is the least electronegative? And that's usually the one in the middle. In actual fact here, the electronegativities of carbon and sulfur are actually very close. but carbon is less electronegative. So we're going to put the carbon in the middle, and we're just going to put the 2 sulfurs at either side. The next step is to build single bonds between each of the peripheral and central atoms. So I'm just going to build a single bond here and a single bond here. Those 2 bonds use up 4 of our valence electrons. So we keep our electron bookkeeping over here. So I'm just going to write it here to the side. So 16 electrons is what we start with. We have 2 bonds. Those 2 bonds contribute 4 electrons, or use 4 electrons, I should say, which leaves us with 12 valence electrons. So we still have 12 valence electrons to use in the building of this structure. So we probably have a little bit more work to do. The next step is to look at the peripheral atoms and figure out whether or not we have a full valence. So I'm going to just draw a circle around all the bonds in the sulfur atom itself. When we look at this, the number of electrons that I've drawn on the paper right now are just these bond electrons here, which is 2 electrons. We know that sulfur needs to have 8 electrons. So in order to give it a full octet, we know we've got 2. If we need 8, we need 6 more. And we're simply going to add these 6 electrons as 3 sets of lone pairs around the sulfur itself. So we now added 3 lone pairs over here. And those 3 lone pairs used 6 electrons. That leaves us with 6 electrons, but now we have a happy sulfur. Has 8 valence electrons around it. Now we're going to check the other peripheral atom, which in this case is this sulfur. And if we draw a circle around it, obviously it's just like the other sulfur was at the beginning. We already have 2 electrons, but we need 8. So we're going to add 6 more in the form of 3 lone pairs. And that ultimately uses the last of our valence electrons. So from a bookkeeping perspective, we've used all our valence electrons. We cannot add any more electrons no matter what we need to do. It's worth remembering that point. So our 2 peripheral atoms, the sulfur here and the sulfur over here, are both satisfied at this point. They both have 8 valence electrons. So let's look at our central atom, which is the last thing we do. And if I encompass all the bonds in the carbon atom here, and count how many valence electrons are around that carbon, well, we have 2 from this bond, we have 2 from this bond, and that is it. So it only has 4 valence electrons right now, but the problem we have is we can't just add any lone pairs because we have no electrons left. So what do? What we typically do at this point is we look to one of the peripheral atoms that has a lone pair, and we use that lone pair to create a double bond with the central atom. So if we look at this sulfur here, it has a single bond and 3 lone pairs. So if we contribute one of these lone pairs, if we kind of push that in to make a bond, what we effectively do here is we form a structure that looks like this. The sulfur is now doubly bonded to the carbon. There are now 2 lone pairs over here on the sulfur. The lone pair that was on the sulfur just created this second bond. The carbon is still attached to the sulfur on the other side in exactly the same way. So I haven't added any valence electrons at this point. All I did was use some that were already present in the molecule. If we check the sulfur over here, it still has 8 valence electrons, right? 2 from that lone pair, 2 from that lone pair, 2 from this bond, and 2 from this bond. 4 times 2, that has 8 electrons. That is still good. So even though we pushed a lone pair in, it's almost like they get double counted. Remember, they're being shared, and that's the point of this. This is a covalent bond or molecular bond. Now on the other side, we have sulfur, because if we check the carbon, we still only have 1, 2, 3 bonds. 2 electrons per bond is 6 electrons. So we still need 2 more electrons to satisfy the octet of that carbon. We could pull them from this side, but more likely they're going to come from the other side. So what I'm going to do now is I'm just going to use this lone pair on top here, and I push those in to create another bond between the carbon and sulfur. And if we do that, we end up with a molecule that now looks like this. Notice now each sulfur has 2, 4, 6, 8 electrons, 2, 4, 6, 8 electrons. So both sulfurs are happy. And now the carbon has 2, 4, 6, 8 electrons. So the carbon also has 8 electrons. So at this point, all of our valence shells are satisfied as well. They all have 8 electrons. We've used all of our valence electrons that were introduced by the elements in the molecule itself. We created single bonds to initially put our structure together, and then we pushed some electrons around here and here in order to create double bonds to satisfy the octet in that central atom that wasn't satisfied right out of the gate. So from a Lewis structure perspective, this is the structure of CS2. Now, what does this look like on a molecular geometry? So if I take my carbon and if I want to create double bonds, so I'm going to use the reds to represent the sulfur. Actually, you know what? Let's use the yellows. Now, even though there's more dots on here than we need, we're going to use the yellows for sulfur. That's the appropriate color. It's not critical that you do that, but so I'm going to put 2 bonds here, and this is how you build a molecular model. You need to use the longer bonds, and then what you do is you simply bend it around so you can plug it in. So that now is a carbon to sulfur double bond. And if I build one on the other side, now we have our molecule carbon disulfide. Right, we have our carbon, we have our 2 sulfur atoms, and notice there's a double bond here and a double bond here. So a couple of things you can do here is you can now look at the molecular geometry of this, and you can see that the 3 atoms, so think about it in terms of the atoms. If we look at these 3 atoms, you would say they're in a straight line. And as such, you would say the molecular geometry of this is linear, right? It's a straight line. What's interesting to note, though, is these double bonds don't line up like mine do on the paper. Notice how they're kind of perpendicular to each other. Notice one's here, and one is kind of going in a plane the other way. If I held it like this, one of the bonds almost disappears. So you can see this double bond clearly. I have to rotate it 90 degrees in order for you to see the other double bond. So even though there's 2 double bonds there, they're not quite laid out the way that I have them laid out on a 2-dimensional piece of paper. So it's worth understanding the geometry is not just about the atoms. It actually also pertains to the bonds, and that has impacts on reactivity, etc., which is kind of beyond the scope of this, but just to give you an idea of some other things this does impact. So this is our molecular model for CS2, and you can see the geometry is clearly linear. And so if it's linear, the angle from here to here to here is basically that angle right there. Obviously the straight line, the bond angle of a straight line is pretty straightforward. It's 180 degrees. So we know that sulfur to carbon to sulfur, that bond angle there is clearly 180 degrees. So a linear molecule like this would have a bond angle of 180 degrees. What about bond polarity? Well, I already said that the difference in electronegativity between a carbon and a sulfur is very little. In fact, very slightly in the direction of sulfur, and I mean very slightly. I think the dipoles are like 2.58, 2.55. So I mean the electronegativities are 2.58, 2.55. They're really close. So even though there might be a very slight polarity in the direction of the sulfur, the reality is it's not very much. And even if it was, that means we'd have an opposing one here. So this is like a tug of war. And if you add these 2 dipoles together, if I've got a dipole going in that direction, and then I add to the end of that a dipole going back in the other direction, clearly I end up where I started. So this would be ending up with a non-polar molecule. So even though the bond has the tiniest amount of polarity associated with it, it's not, we would never consider it a polar bond, but it just has just a slight dipole. Overall, the molecule here would be nonpolar. You could argue the bond there is nonpolar, therefore the molecule is nonpolar. When the polarity is that small, remember, you need polarities of a polarity difference an electronegativity difference of 0.4 or greater in order to be considered a polar bond. If it's less than 0.4, you would normally consider that a non-polar bond. So in this case here, this is a non-polar bond. And consequently, you normally have non-polar molecules. So now you should be able to answer how many valence electrons you had. You should be able to come up with a reasonable Lewis structure. You can then build the actual molecular structure using modeling kits. You can determine the molecular geometry for this, which we said was linear. From that, we can then determine the bond angle in that molecule. And there's only one bond angle, S to C to S. It's 180 degrees. We can determine whether or not the bond is polar or not. Well, this is a non-polar bond, and that ultimately will lead to non-polar molecules. So we're going to put this one away. And the next one you're going to do all the hard work on your own. And once you've done that, I'm just going to build the molecule for this one. And you can figure it out yourself. So the next molecule I'm going to build is H2S. So go ahead, pause the video here, and I want you to work through everything you did up here. This is really important. Being able to do this is critical in understanding the geometry of molecules, because ultimately that impacts their reactivity, their solubility, all sorts of things. And so I want you to go ahead and figure all of that out for H2S, and while you're doing that, I'm going to build the molecule and I'll present it to you. All right, so you should be done with that now. So this is the molecule H2S. Oh. So this is H2S. It's a little bit hard to see. These little guys on top are hard to see, but what you should have determined is that you have a sulfur in the middle, you have the two hydrogens on either side, and you have these two lone pairs. That's what the little stubby bits represent. That's a lone pair of electrons. So when you've drawn it, you should end up with something that looks some version of this, where you can see two lone pairs on the sulfur and two hydrogens on singly bonded to that sulfur. So from this, you can now determine both an electron domain geometry, which is considering all four. The electron domain geometry for this would obviously be tetrahedral. We have four pieces relatively equally spaced, not perfectly equally spaced. But you can also find the molecular geometry where you don't consider these lone pairs. You simply consider only the actual atoms present. So if I cover up those lone pairs, these are the atoms that are present, the two hydrogens and the sulfur. So looking at that, you should be able to determine a molecular geometry. And from that, you should then be able to determine this bond angle here. All right, so the next one I want you to attempt is nitrogen, N2. So molecular elemental nitrogen is N2. A lot of elements are just single atoms when they're in nature, but there are some so-called diatomics, those that have two atoms present, and N2 is one of those. So I want you to determine the structure for nitrogen through using the Lewis structure method that we were doing earlier. All right, so once you're done building nitrogen, it should look something like this. You got your two nitrogen atoms, and between it you have a triple bond, but you also still have a remaining lone pair on each of the nitrogen atoms themselves. So when you do your valence count for that atom, that nitrogen right there, you have 2 from the lone pair and 2 from each of those 3 bonds. 3 times 2 is 6, plus the 2 from the lone pair is 8. Of course, that's true of the other one as well. By looking at this, you should be able to figure out linear geometry. You should be able to figure out the molecular geometry for this, and I just gave it away. It's linear. For now, you should be able to get the bond angle here. Can't really have an angle between 2 points. And then ultimately, you should be able to figure out whether or not this bond is polar or not, and therefore whether or not the molecule as a whole is polar. The next one I want you to look at is SO4 2-, but I'm going to work through this example with you because this is the first time we've seen one where there's a charge present. How do we calculate the valence electrons for this? Well, we start by doing the same thing. We say to ourselves we have a sulfur present, we have an oxygen present, but we also have a 2- charge present, right? I'm just going to treat the charge separately. Sulfur contributes 6 valence electrons, oxygen contributes 6 valence electrons, and the 2- charge technically contributes 2 valence electrons. There is 1 sulfur, there are 4 oxygens, and there's only 1 of the 2- charge. So if we do the math for that, we end up with 32 valence electrons available for us to build our structure. Our next logical step is to build the rough structure, which is with the least electronegative element in the middle. Well, that would be sulfur. Now I'm just going to place the 4 oxygens around it. The 2- charge really only comes into play because it's a part of our valence electron. We don't need to draw it in this structure per se. Then we're going to draw our 4 single bonds. So we're going to subtract 4 bonds. That would be 8 electrons altogether. So now we have 24 valence electrons remaining. And then we're going to start checking our peripheral atoms. You're going to notice that each oxygen has 2 electrons from the bond and nothing else. Oxygen wants 8 electrons, so we're just going to give it 6 electrons from 3 lone pairs. So if we subtract 3 lone pairs here, that will be another 6 electrons. That will leave us with 18 electrons. We're going to do the same here, so minus 3 lone pairs, minus 6 electrons, that leaves us with 12 electrons. And I'm just going to do these 2 together so we don't just keep doing this all day. There's 3 more lone pairs. There's a total of 6 more lone pairs. So if we do 6 lone pairs, that's the remaining 12 electrons. We have now used all of our valence electrons. We have satisfied peripheral atoms. Now we just got to check our central atom, the sulfur. Well, here we have 2, 4, 6, 8 electrons. The sulfur is also satisfied. So in terms of our general structure, we're in a good spot. The only thing we have to do is understand really where this 2- charge is. We can cheat if we wanted to, and we could just put a square bracket up here and write 2-, but that's the cheat way out. One of the things we can remember from reading in the book, doing our classwork, is that sulfur can have what we call an expanded octet. It can actually hold more than 8 electrons. So if we do this, the question is, what is the net charge on each atom? What is the formal charge on each atom? Remember, we have to calculate formal charge. We take the number of valence electrons for that particular atom. We subtract the number of lone pair electrons, and we subtract the number of bond electrons divided by 2. There's lots of variants of this equation, but they ultimately come to the same calculation. So if we look at here, so I'm just going to call oxygen 1. So oxygen 1, if we calculate the formal charge, valence electrons for oxygen is 6. The number of lone pair electrons in this case is 6. And then the number of bond electrons is 2. And we're going to divide that by 2. So it's going to be 6 minus 6 minus, and that's 1. 6 minus 7 is equal to a formal charge of minus 1. So technically this oxygen has a minus 1 charge, and since all 4 of these oxygens are the same, each of those are a minus 1 charge. Let's look at the central atom sulfur. So I'm just going to call this Fc. Sulfur starts with 6 electrons. The sulfur in this case has no lone pair electrons, but it does have 8 bond electrons, and we divide that by 2. So that's going to be 6 minus, so this should be, I apologize, these should be pluses here. Six minus 0 plus 4, so that's 6 minus 4, and 6 minus 4 of course is a positive 2. Notice here this was very specifically minus 1. We have to be careful with that sign. That means the sulfur has a formal charge of plus 2. Now, the good thing about this is it works out, because if I've got a plus 2 and 4 minuses, my overall charge is minus 2, which is what we had originally. So that's a good sign. That means we're doing good work. However, this is probably not the most stable form of this molecule. Once you get into charges like this, we have to start considering some other possibilities. As a general rule, nature is not a big fan of charge. We like to try and remove these point charges, and we try to like smooth them out a little bit through the molecule. So how do we do that? Well, when you have a peripheral atom that has a negative charge and has a lone pair, and you have a central atom that's got a positive charge, just like we did when we ran out of our valence electrons, we were pushing lone pairs in to make double bonds and so forth. We're going to do the same thing here. So I'm just going to redraw this molecule exactly as it was before we did the calculation of the formal charge. And now what I'm going to do is I'm just going to take one of these oxygens. It really doesn't matter which one. I'm going to take these oxygen electrons here and I'm going to push them in to the sulfur. And what that will do is it will create a double bond between the sulfur and the oxygen. It will leave 2 lone pairs on that oxygen, still got 8 electrons. This oxygen is going to look the same, this oxygen is going to look the same, and this oxygen is going to look the same. Each of these oxygens still has 8 valence electrons around it. The difference is now the sulfur has 10 valence electrons, 10 valence electrons, which is okay. So if we do this, if we calculate formal charge now, these oxygens here haven't changed. There's still a minus 1 formal charge. But what about the sulfur and the oxygen? So the sulfur formal charge now, we start with 6 valence electrons. We know it has no lone pairs, and we know it has 10 bonding electrons that we're going to divide by 2. So you can replace this statement with number of bonds if you want. That's another way of looking at this. So 6 minus 5 is just plus 1. So now the charge on the sulfur has been reduced. That's a good thing. If we look at the oxygen formal charge that has the double bond, it starts with 6 valence electrons. It now has 4 lone pair electrons, and it now has 4 bonding electrons that we're going to divide by 2. That's going to equal 6 minus 4 plus 2, which is going to be 6 minus 6, which is 0 formal charge. So what we've done by moving those lone pair in, we've still satisfied the valence shells, because sulfur, remember, can have an extended valence shell. So it's got 10 in its valence shell here, but that's perfectly okay. The oxygen still got 8, and the other 3 still have 8. So this, as from the perspective of Lewis structures, if you want, this is still a perfectly good structure. But what we've done by pushing that lone pair in is we've reduced the overall charge dissipation in this molecule. If you look over here, we had a +2 in the middle, then we had 4 -1 point charges around it. That's a lot of charge. By doing this, we actually reduce the charge on that sulfate molecule, or sulfate ion, I should say. What if we did one more step? What if we took another one of these lone pairs and pushed them in? If we did that, we would end up with a structure that looked like this. Right, all I did was take one of these lone pairs and push them in. If we took the formal charges of these would still be -1. They haven't changed. We know that an oxygen that looks like this has a formal charge of 0, has a formal charge of 0. So the only one we need to calculate to be sure is the sulfur formal charge. Now it has 12 valence electrons. That's the most it can hold. But it starts with 6 valence electrons. It has no lone pairs. It is now a part of 1, 2, 3, 4, 5, 6 bonds. So it's got 12 bonding electrons, and we're going to divide that by 2. So now we have 6 minus 6, which is 0. So now the sulfur has a 0 charge. So we've reduced the charge even further. And so at this point, we would consider this to be the best structure of a sulfate system, because it has the reduced formal charge, or at least the reduced point charges. And the net charge, which is 2 minus at the beginning, is still 2 minus here, right? Because we've got 3 zeros, a -1 and a -1. That's a -2 charge. You'll note that at every point through this process, we always have a net -2 charge, right? We started with a +2 and 4 minuses, that's -2. We had a +1 and 3 minuses here, that's -2. Then we have 3 zeros and 2 minuses here, it's -2. So we know that the work we've been doing is correct, because that net charge has never changed. And the valence shells of every atom has always stayed consistent. And then beyond that, we've been able to we've taken this sulfur and we've now maxed out its valence shell to 12. We can't add anymore, so we can't do this one more time, because in doing so, we would actually be then disobeying our laws of valence shells that we live by in creating these molecules. So this is how we do SO42-. So if we were to build this, the sulfur is usually yellow. I'm going to use these silver ones though that have 6. So since we've got 6 bonds in that central sulfur, we do need to make sure that we have sufficient spots for all those bonds. So we're going to use a central atom that has that. And then we're going to put 6 oxygens around the outside. So this is what we're starting with. Something that has 6 potential records. There's 6 bonds here. So I've built the 6 bonds. These longer ones are going to bend to be my double bonds. And the other 2 are going to be the short, stubby single bonds. And then I'm going to put oxygens on here. And I'm going to make it as close to representative as possible. So we'll bend in the double bonds. And on those single bond ones, remember we have an extra lone pair versus what we normally start with. So I'm just going to put that extra lone pair in there. There's 3 lone pairs in oxygen technically. But I'm going to show that extra lone pair, because they all have 2 lone pairs, and then these 2 guys have the extra lone pair. So if we look at this molecule now, like if you're trying to get an approximate geometry from this, it looks just like a skewed tetrahedral. The only reason it's not a regular tetrahedral is because you have 2 double bonds and 2 single bonds. So it is tetrahedral-ish in nature, but the bonds are just a little off because of the way we have to build it with this. So you can get your general molecular geometry by looking at this. And then what you're going to figure out is, even though we're showing different kinds of bonds here, the reality is, at any given time, any one of these could be the double bond, and any one of these could be the single bond. It's constantly moving. So this resonance is what they call that. This resonance that exists actually creates 4 fairly identical bonds. So even though we potentially have 2 doubles and 2 singles, 2 doubles and 2 singles, the reality is if we were to create a hybrid of all 4 possibilities of this, all possibilities of this, it would look like this, right? Where each of these bonds are like 1 and a bit bonds, but we just don't really talk about it like that. So this is what it looks like just for a moment, but then a moment later, it looks like this, or it looks like this, right? So it's constantly, these bonds are constantly moving, these electrons are moving around. But if you're trying to build the model, this is what it looks like. If I just kind of bend that back a bit, we have a true tetrahedron.